So good afternoon, everyone, and thanks for joining us today. Our Zoom program today will be hosted by Dr. Ryan Chatbolt. He's from Michigan State University's Department of Geography, Environment, and Spatial Sciences. He's here to lend his expertise on the very important topic of climate change. If you have any questions for him as we go along, please make sure that you put them in our chat box down below. And he's going to get to them as he gets a chance. And without further ado, here's Dr. Ryan Chatbolt.
Right, hi everyone. Welcome to this Zoom experiment with this Understanding Climate Change lecture. I've been doing this lecture on and off for the last couple of years. I'm born and raised in southern Michigan. Did my undergraduate degree at CMU and both my graduate degrees at Michigan State. After that, I did a 2-year research position at Michigan State. It was a joint position with the U.S. Forest Service. And then I taught full-time at Saginaw Valley and CMU. Did a part-time adjunct position at Oakland Community College in Farmington Hills. And then 2017 to 2019, I was an assistant professor at Northland College. Helped get them to the point now where they have a climate science degree program that they're now offering that became effective this past fall. I am now back at Michigan State University as an advising specialist. My position is split between advising, teaching, and outreach, and this is part of my outreach portion here today. This lecture kind of started with a guest lecture I did at Northland College a couple of years ago. I also developed a course titled Understanding Climate Change, which is kind of the title for this presentation. It's going to be split into 3 parts today. We're going to look at the symptoms, the science, and possible solutions. Climate change is a messy topic. It's not always clear and obvious how we determine what is or is not climate change. And part of this is that there's a wide spectrum on a time scale, everything from what happens to changes in atmospheric conditions on the order of seconds, minutes, hours, and days. We usually refer to that as weather. Once we're starting to get out beyond, say, 2 weeks, especially once we get to monthly, yearly, and decadal scales, then we can start to think about those atmospheric conditions as climate and perhaps climate variability or climate change. And there's certainly a lot of fuzzy area between what is climate variability versus climate change. This is one example. This is from Fairbanks, Alaska, looking at 2 different time periods. Each of these is 30 years in length. This is a common benchmark that we use in climate science as we monitor change over a minimum of 30 years. The older period from 1900 to 1929 is the black solid line. This is showing us the frequency the different temperature values occur. These are going to be in Celsius. You see the peak at 10 degrees Celsius, that's equivalent to 50 degrees Fahrenheit. So that's their most common temperature, and then we should see it trail off in both directions, kind of creating a bell-shaped or Gaussian curve. So that was at the beginning, first 30 years of the 20th century. And then if we take the last 30 years of the 20th century, that's the gray line, 1970 to 1999, we can see that essentially the bell entirely has shifted to the right by about 2 degrees Celsius, showing us that the frequency, the peak of that curve is now around 12 degrees Celsius, and you see some of the highest values now extending out to about 20 degrees Celsius. This is just one example, but we see this over many areas on the planet. It kind of shows you how the entire distribution of temperature has shifted, but you can still see that cool temperatures still occur. You can see that moderate temperatures occur, and we can see that there's an increased frequency of higher temperatures. Now focus on the top half of this figure with me first. This is looking at global surface temperatures. So it's essentially taking all of our surface thermometer stations across the globe, both over land and over oceans. It's averaging those values. We've removed the seasonal cycle. So that's why it says annual average. So it helps remove some of that annual noise of the seasons. That is the thin gray line that you see. And you can see that there is interannual variability, fluctuation from year to year. This is dating back to 1880, taking us close to the present. And then if we smooth that line even more using a 5-year running average, that kind of helps take out some of those peaks and valleys and kind of shows you the overall trend. And I hope that you can also see that we generally had decreasing temperatures in the late 19th century into the early 20th century. And then from about 1910 to 1940, the trend was generally upwards. Then we had a period of kind of stagnant temperatures from around 1940 through the 1970s, and then it's been on a upward trend since the mid-1970s. That's the global picture. This is why we might sometimes use the phrase global warming, but there is some confusion with that because not every single location on the planet is warming. Of the areas that are warming, they're not all warming by the same amount. And we do have still cool temperatures that occur, cool months that occur, and cool years that occur. So the term global warming is not a particularly good description of what we see here, but you do see that the general trend has been upwards. If we look at this on more of a regional scale, so this is the bottom half of the figure, this is looking by line of latitude. If we focus on the higher latitudes of the northern hemisphere between 24 and 90 degrees north latitude, that's the thin solid line. If you're looking at areas in the tropics, close to the equator between 24 south and 24 north, that's the dotted line. And then if we're focusing on the mid and high latitudes of the southern hemisphere between 24 and 90 degrees south, that's the dashed line. You can see that all three still reflect the same global trend, generally cooling early on, then warming. In the early 20th century, stagnant temperatures in the mid-20th century, and then warming since the mid-70s. But the higher latitudes of the northern hemisphere jump out. You can definitely see that the trend there, especially since the 1980s into the 1990s, you can see that that trend is different from what we see in the lower latitudes and in the southern hemisphere. And we can illustrate part of the reason why by looking at the globe either from above the northern hemisphere or above the southern hemisphere. Certainly our planet is mostly covered by ocean, about 70%. But of the land mass that we possess, most of it is in the northern hemisphere. We have North America, Europe, Asia, Africa here in the northern hemisphere. That land has a different potential for heating and cooling compared to water. Land tends to heat and cool more rapidly. Water takes a slower time warming up because it has a higher heat capacity. The other thing that's different is at the highest latitudes at the Arctic, it's essentially the Arctic Ocean surrounded by land masses. And what we see in the southern hemisphere is the Antarctic landmass surrounded by water. So there's a contrast between what happens at the South Pole versus the North Pole. And we'll see a little bit later why the Arctic, this ocean that is comprised of a lot of ice surrounded by landmass, why that is a very important player in the climate change story. This is the area where we see temperatures warming most rapidly on the planet, which at first glance takes people by surprise. Doesn't make much sense why the Arctic is warming more than other areas, but that is in fact the case. Thermometers confirm that for us time and time again. Okay, so what we're looking at here is this is temperature, and as temperature goes up, this is going to have consequences for what we see in regards to ice on the planet. And we can describe this in a variety of different ways. I'm going to show you at least several of these, kind of building up to where we're going at, talking about climate symptoms in this section. This figure is looking at the mean length of glaciers, and we're grouping these by 5 different categories, both northern and southern hemisphere. And so this is the mean length of glaciers in meters relative to their 1950 value. And we see that the mean length of glaciers remained pretty steady from 1700 through the mid 1800s. And then since the middle part of that 19th century, mean glacier length has decreased steadily for all 5 of these regional groupings. And that continues through the present. Now, if we can look at specific glaciers, especially over the Antarctic continent, where we can find some examples where glaciers are growing, but this is looking at overall, the big picture here. Most of them are shrinking on a global scale. Next figure now is looking at mean ice extent at the period of the year when we tend to see that ice extent at its annual minimum, which in the Arctic is usually in the month of September, because we've just closed out the summer season. We've had maximum melt by that time, and then glaciers are going to start gaining in mass again as we roll into the fall season. This is looking at 1979 through the present. It's not a particularly long data set, and the reason for that is that we obtain this data from satellite imagery. Most of that dates from the late 70s through the present. So we are restricted by a short time period, but the trend here is clear. This is looking at ice extent or ice area in millions of square kilometers, and we can see that the trend has been steadily decreasing. There is some variability from year to year. The scale here on the vertical axis does not go all the way down to 0 on this figure, but if we were to assume that this trend was to continue and extrapolate out forwards in time, we would approximately reach 0 around the year 2070. There's a lot of unknowns of what could happen between now and the next 50 years and whether or not that will come to fruition. Another way that we can look at this is through cumulative ice loss instead. So we should see kind of an inverse curve of what you saw in the last figure. So we should see, if we're talking about ice loss, we should see the value go up with time. That's indeed what we see. This is in billions of tons for the units on these numbers, and this is taking us through 1992 through close to the present. And we see the ice loss value gaining rapidly, especially since the year 2000. Now, the surface temperature values I showed you a few slides back when we were getting started, that's going to be biased by thermometers that are present on land, just because most of our weather stations are land-based. We do have buoys and other instrumentation on the oceans. But if we focus just on ocean temperature, so that's what we see here, this is from late 50s through 2010. This is showing us temperature anomalies relative to 1970 to 2000 for its base period. You can see that the temperature anomalies are small. Ocean water doesn't change temperature all that much because the volume is so enormous. It takes a long time for ocean to cool down and warm up. But there is still a trend. Although these are small numbers, you can see that ocean temperature overall has been increasing, especially since the 1970s, which kind of closely mimics what we saw in the overall surface temperature record a few slides back. So adding all these things together, we've seen that glacier length has decreased, we've seen that ice extent has decreased, ocean temperatures are going up. All of these things in combination suggest to us that ocean or sea level should be increasing with time. Water, as it warms up, as we see here, is going to expand by thermal expansion. If we're losing ice in our glaciers, that's going to be adding liquid water to the ocean. So the ocean volume should increase, which would be, for us, reflected in sea level rise. And that's what we see here. Units are in millimeters. This is from the mid-1990s through 2014, it looks like. And you see a steady upward trend, some variability from year to year, but the trend is obvious that it is increasing. Because of coastal shape, sea level rise does fluctuate regionally, actually quite a bit, but this is looking at a global average. Okay, so that's the picture. Temperature increases, ice loss. Oceans are increasing in temperature, oceans are increasing in volume, which results in sea level rise, which is going to have ramifications for coastal erosion and also for aquatic species. It's going to have impacts on how tides and coastal flooding, especially during tropical or like hurricanes and tropical storms, those events are going to have a greater impact as sea levels increase. So those are direct measurements from our instrumentation. To give us more context about Earth's climate history, we really want to understand what has happened over the last 4.5 billion years that our planet has resided in our solar system. We are restrained by the fact that thermometers, that technology is only a few hundred years old. The network of weather stations only really takes us back to the late 1800s. If we want to look further back in time, like this figure here in Celsius, it's showing us Earth's approximate temperature going back 70 million years. Present day is on the far right-hand side. And at first glance of this, you're going to see, well, the coolest temperature is in the present day at the far right-hand side. It does not look like a warming climate is what we should be concerned about. And you can see that throughout Earth's history, at least over the last 70 million years, temperatures have in fact generally been warmer than they are today. Okay, so how do we determine these approximations for temperature? We did not have thermometers measuring temperatures 70 million years ago. We have to rely on other types of hints that the natural environment provides for us. Some examples would include looking at tree ring analysis and pollen analysis. That type of science can take us back on the order of hundreds into thousands of years ago. Some of the oldest trees, like bristlecone pine, can live to be 10,000 years old. So that still doesn't take us very far on this figure. We can also use ice core analysis. Ice is going to contain oxygen isotopes. The ratio between oxygen 16 and oxygen 18 can be used to approximate global temperature. The ice also contains air bubbles, which gives us a good idea of what the atmosphere's composition was at that point in time. Ice cores give us a very good estimate of temperature. And those can take us back as on the order of tens to hundreds of thousands of years before the present. The current record for ice cores takes us back, I think, 800,000 years. But that's still going to be restrained to the far right-hand side of this figure. So we're talking about millions on the time scale here. If we want to go back millions of years, like you see on this figure, we have to rely on geologic lines of evidence. So that's going to be sediment cores and rock information. That, again, using oxygen isotopes can give us an approximation for global temperature. Historically, we can see this PETM that stands for the Paleocene Eocene thermal maximum. We reached a high temperature there about 55 million years ago, and temperatures have generally cooled over the last 55 million years. This is why sometimes you will read or hear that we are technically still in the midst of an ice age, and this figure reflects that clearly. Now the big gray bar on the right-hand side, we're going to now zero in on that. That's looking at just the last 4 million years, only 4 million years, which is a blink of an eye on a geologic time scale. Over on the right-hand side, this is those oxygen isotopes, O18, that I was referencing a few moments ago. So over the last 4 million years, we can now see a lot of the variability from year to year, and you can see that the trend has still generally been downwards. What we refer to as the Pleistocene epoch is, depending on which textbook you read, defines it as starting somewhere between 1.5 and 2.5 million years ago. So about in the middle of this figure. And during that time was generally glacial advance. And on a smaller time scale, because you can see all of the peaks and valleys in this temperature, you can see that there were still periods of warmth and periods of cold temperature, and none of those periods lasted for very long. So there were very rapid changes between glacial advance and glacial retreat on a geologic scale. Most of those peaks and valleys are separated by about 41,000 years. And in a few slides later on, we'll hopefully understand a little bit better why that fluctuation happens every 41,000 years. More recently, though, you can see that the variability has increased. That distance and temperature between the high temperature and cold temperature seems to be increasing, and the frequency between the peaks is increasing. In more recent years, those peaks have reoccurred more like 100,000 years apart rather than 41,000. We're going to take a look at the gray bar here. We're going to zero in on the last 400,000 years. This is now well within the reach of our ice core record. And this is now showing you temperature in the bold solid line and carbon dioxide concentration in the atmosphere in its units of parts per million. And you can see that the two very closely coincide. It's not a perfect fit, but it's very close. And the reason why we are illustrating this point to you is that carbon dioxide is usually considered to be the most important greenhouse gas that human behavior contributes to. Now, certainly throughout most of this period, human population was very small, except for the very right-hand side here where we're in the present day. And you can see on this figure, even what we reflect as the present day is still within the range of what we've seen historically in terms of both temperature and carbon dioxide. You can see that carbon dioxide here is overshooting the trend for temperature. The other thing that's of interest, if we're following the idea of natural cycles repeating again and again, you can see that we've gone through these periods of rapid warming and then gradual cooling. This has happened multiple times with some other smaller peaks here in between, but you see rapid warming and gradual cooling repeating itself time and time again. And if anything, it suggests where we are here on the right-hand side in the present day, that we should be expecting another gradual cool down going forward. What we understand in regards to our geologic evidence and also the interactions between the Earth and the Sun, that is indeed what should be commencing sometime soon, but so far that hasn't been the case. Let's focus in on now just the last 11,000 years. This is now referred to as the Holocene Epoch. And we see warming here starting about 11,000 years ago, and then a nice plateau of warm temperatures, lasted about 5,000 years. Then we had a gradual cool down, and now rapid warming here over the last couple centuries. And this is really what we were reflecting in one of our earlier slides when we were looking at Earth's temperature for the last 150 years. So that takes us through the present day. That's the big picture. The gray area that you see on this figure is kind of showing us our degree of uncertainty, just because most of this is not measured from actual thermometers, unlike what we see here at the far right-hand side. All of this is reflecting the uncertainty based on our ice core analysis primarily. So that's our first section on the symptoms. I'm going to pause for a moment, see if there are any questions out there. You can feel free to plug those into the chat bar if you want. I'm happy to address these at any point as we go along, or we can also look at questions once we are done today.
Doesn't look like we have any questions just yet.
Okay, I'll plug along then.
If the chat's disabled for anybody, you can go ahead and put it in the Q&A and I'll make sure that it makes it into the chat.
Looks like someone raised a hand. Looks like it went away. Garrett. Where'd you go, Garrett? I'm going to allow Garrett to talk if Garrett wants to. Garrett, if you have a mic on, you should be able to speak, or you can type something into the chat bar.
Yeah, maybe it was just a accident.
Okay.
Chat.
Okay, well, I'm going to move ahead. So we're going to talk about some basic climate science. This is probably my favorite part to talk about. This is all going to be all about trying to understand why is Earth warming. At least that's what the thermometers are telling us right now. Physics, basic physics tells us that every object is emitting energy. Our bodies, your computer, your coffee mug, your smartphone, your pad of paper on your desk, everything is emitting some amount of energy, and it could be of these various types that you see on the figure here. It could be ultraviolet, visible energy, infrared, etc. down the list. An object's temperature is directly related to the wavelength of energy that it emits. Here are a few examples. If we look at the top left of your figure, these 4 objects are in Kelvin temperature. I know we're usually familiar with Celsius or Fahrenheit. Kelvin is essentially the Celsius scale, but we've made everything a positive number so that there aren't negative numbers. So these numbers look large. To give you a sense of some baseline values that we could be familiar with, an approximate Kelvin temperature for Earth would be 300 Kelvin. The approximate surface temperature for the sun would be 6,000 Kelvin. These values fall somewhere in between. And we can see that each one of these objects, the hotter it is, the more power it's emitting, and also the hotter the object, the peak of its curve shifts toward the shorter wavelengths. If we were to have the value for the sun plotted on here at roughly 6,000 Kelvin, its peak of its curve would be around 0.5, which is right in the middle of the visible spectrum. This is why we see those colors of the visible spectrum. The sun also emits energy in ultraviolet and infrared, if I go back here. So the sun's energy is mostly within this range. Earth is, in comparison, much cooler, around 300 Kelvin. Its peak is closer to 10 microns. And its peak falls, therefore, within the infrared spectrum. So this is why we use infrared technology to measure surface temperature of Earth. That's what our satellites rely on. We can use infrared technology to measure the temperature of our canine friend here. We also rely on infrared technology for the thermal thermometers that you use to measure. In my case, we have to measure the temperature of our toddler. We're doing that regularly now in the midst of this pandemic. You use the thermometer that you point at your forehead or you touch on your ear. It gives you an immediate temperature readout, but what it's actually measuring is the power that your body is emitting, and we can relate that to temperature, as you see in the figure at the bottom. It's a nice exponential relationship that as temperature increases on this Kelvin scale, the power emitted goes up a lot. We understand the dimensions between the sun and the Earth. We know that they're both spherical objects. The sun is much, much larger. We can reflect their size based on their radius value. We know the shape of Earth's orbit around the sun. It can be close to a perfect circle. It can also change to a more ellipse shape. The average distance is about 150 million kilometers, but there is some small fluctuation in that throughout the year and also fluctuates over much longer time periods. We know that Earth rotates on a daily cycle. We know that its axis is tilted, actually off to one side by 23.5 degrees. And it's that axial tilt that is actually the most important contributing force to our seasonality as we make our journey around the sun, because that tilt impacts the solar angle and how it strikes Earth's surface. Excuse me, I'm going to take a quick drink. So what we are measuring with our instrumentation is that power that is emitted by the sun that reaches our atmosphere. And then we can use a mathematical relationship to convert that to a temperature. And that's why we're able to estimate what sun's surface temperature is, even though we've not actually measured it directly. So this is a depiction of solar energy illustrated by our kind of yellow-orange arrow. It's striking the top of the atmosphere. What we're trying to understand is what happens to that energy once it enters the atmosphere. Some of it's going to be absorbed by clouds, by dust, and by gases. Some of it's going to be reflected by the clouds, the dust, and the gases. Some of it's going to be reflected by Earth's surface. In fact, ultimately, on average, about 30% is reflected. So it's totally lost back to space. So that means we have 70% left on average that's going to be absorbed. And about 20% of that gets absorbed by the lower atmosphere. And the remaining 50%, again, this is on average, depends on the season, depends on the time of day, depends on the cloud cover. But on average, about 50% gets absorbed by the ground. There, it's going to heat the ground. It's going to heat the lower atmosphere, keeps us warm. We can measure that directly with a thermometer. Once that energy has been absorbed by Earth's surface, Earth will later re-emit that energy. But because Earth is a much cooler object than the sun, that energy is emitted at a longer wavelength. So instead of it being mostly visible energy, it will be mostly infrared energy that Earth emits back. Some of this energy that Earth emits back will be directly lost to space. Some of it is going to heat the lower atmosphere. Some of it is going to be absorbed by the gases in the lower atmosphere. These gases specifically are what we refer to as the greenhouse gases. Greenhouse gases include water vapor, carbon dioxide, methane, nitrous oxide, and there's some others. Water vapor is actually the most common, and its quantity doesn't change much in the atmosphere. Human activity plays very little role in its concentration in the atmosphere. And water vapor, it's part of the water cycle, doesn't spend much time in the atmosphere before it returns back to Earth's surface through condensation and then later precipitation. So its impact over time doesn't change much. The other three that I listed, carbon dioxide, methane, and nitrous oxide, all three of those occur naturally, but also all three of them can be contributed to by human activity. Carbon dioxide, methane, and nitrous oxide are all added to the atmosphere through human action, mostly through our energy consumption, whether it's for electricity, for transportation, or for home heating. For example, natural gas that we use for home heating is methane. Nitrous oxide is produced through transportation primarily. Carbon dioxide is produced mostly through energy generation, especially from coal combustion, but it's also produced through transportation, through home heating. Carbon dioxide is by far the most common of those three that I just listed, carbon dioxide, methane, and nitrous oxide. So let's take a look at carbon dioxide here, and we'll look at the top third of this first. This takes us back 10,000 years. The units here are in parts per million. So if you imagine taking a sample of air and dividing that sample into 1 million equal parts, this is the number in parts per million. That's how we represent carbon dioxide most frequently. You can see that the trend was fairly stable over the last 10,000 years, around usually between 260 and 280 parts per million, or ppm. And then you can see here in the last couple hundred years, the value has gone up steeply, and this really closely coincides with the Industrial Revolution. If we take a look at just the last 250 years, you can see this again. The scale is going to increase here, 1750 through the present. Our current value today is around 410 parts per million for carbon dioxide. If we look at just the last 60 years or so, that's what we have here on the bottom figure. Now there's two lines in this case. We'll look at the gray line first. This is showing us what the atmosphere's concentration of carbon dioxide would be if none of it had been removed. So based on human emissions, if it was entered into the atmosphere and not taken back out, what would the value be? And we should, in today's value, be somewhere close to 500 parts per million. That's not what it is. What we actually measure is what you see in this seesaw line down below. There is an inter-annual variability that you see due to photosynthesis as plants and trees absorb carbon dioxide during their growing season. This is going to be dominated by the northern hemisphere, because remember, the northern hemisphere has most of Earth's land mass. So we see an annual trend there based on photosynthesis. The plants are absorbing some of the carbon dioxide, but you can see we are taking up roughly half of what has been emitted, and that is mostly being absorbed by the Earth's global oceans. So that is a good thing for us, that much of what we have emitted, at least approximately half, has been absorbed over time. There are some consequences for the ocean because of that, because carbon dioxide plus water equals carbonic acid. So the pH of the ocean has decreased over time, and this has been felt, the impacts have been felt by marine life, and especially coral reefs. If you hear about or read about the bleaching of coral and the loss of global coral, this is why. Carbon is also contained within methane, that's CH4. If we look at methane over the last 10,000 years, much of the same story, exponential growth during the Industrial Revolution. If you focus in on the last 250 years, you can see that again. This is also in parts per million, and you can very quickly see that the values for methane is much, much smaller. Remember, carbon dioxide today is around 400. Value for methane is around 1.8 parts per million. So the quantity of methane is much, much smaller in comparison, but the warming potential of a methane molecule is on the order of 25 times greater than what it is for carbon dioxide. That sounds dangerous, but the good news is that methane has a much smaller concentration. So usually emphasis remains on carbon dioxide, and you can see that illustrated in this figure. This is referring to something called radiative forcing. These are added watts per square meter based on human activity. Carbon dioxide makes up the largest value here, on the order of 1.8 added watts per square meter from carbon dioxide alone. Methane, although it has a greater warming potential because its concentration is so small, you can see that it makes up maybe 1/4 or 1/5 of the impact that carbon dioxide does. And so this is why our emphasis is usually on carbon capture, carbon tax, all of these ideas of trying to decrease carbon dioxide emissions. Because if we can control that, then they'll have the biggest impact overall. Here's nitrous oxide that I mentioned earlier. Its impact is even smaller. That's why most of you probably haven't heard about it as a greenhouse gas. Ozone is a greenhouse gas too, that we contribute to, but again, it's on the smaller range of values compared to carbon dioxide. There are some impacts that do have a negative. Most of this is solid pollution like dust. Natural sources would be from natural wildfires or from volcanic eruptions. That actually, because it's solid material in the atmosphere, it blocks incoming sunlight and can actually have a cooling impact. Okay, so someone asked, is methane because of a farming boom? Yeah, we're not talking about, I didn't talk about the source of methane, but farming does have a lot to do with that. Part of it is about the types of agriculture. Rice farming produces methane. Husbandry, like cows in particular, produce a lot of methane. Livestock in general all produce it. We produce methane. Even insects like termites can produce methane, but agriculture and now the growing emphasis on natural gas as a fuel. You've all heard of fracking, which is the short term for hydraulic fracturing. That is going to be responsible for some methane emissions now today. Another area of concern with methane is that a lot of it has been frozen in permafrost for long periods of time, and as we see permafrost now starting to melt, we are seeing methane emissions going up in those formerly frozen areas. Okay, so next I want to talk about climate change forcings. What are the things that can impact makes a change to Earth's climate system that's going to result in a change in temperature? And we can really group these into 5 categories. The first of these I call geologic. This is going to be everything from potential meteor impacts, which would be catastrophic, volcanic activity, which has both short and long-term impacts. The short-term impact would be the solid material emitted by a volcano, which is actually going to cool the planet. The long-term impacts from volcanoes would be the greenhouse gas emissions, and mostly in the form of carbon dioxide, which would have long-term impact of warming Earth. And then we also have the land cover change that is a result of continental drift, or the more common term for that is plate tectonics. So as Earth's plates actually shift and the continents move, they are in fact moving still now on the order of centimeters per year. But as the continents move, climates do change, but that's going to be on the order of millions of years. It can't help us explain what's going on currently. The next are solar cycles. And we can look at this in terms of very long-term trends in solar brightness. And the sun has increased in its brightness over its lifetime. It's going to continue to do that until eventually it's going to engulf Earth and most of the solar system. But that's going to take billions of years for that to complete itself. If we're looking on shorter time scales, then we're going to be focused on the sun's sunspot cycle, which repeats roughly every 11 years. And you can see 3 cycles of that illustrated here since 1980. And you can see in more recent years, especially since around 2000 or so, sun's brightness has decreased with time. So that actually does not help us understand warming trends that are going on currently right now. We can also look at the relationships between the sun and the Earth. I've talked a little bit about the shape of Earth's orbit. It's not a perfect circle. It's more like an ellipse in shape, and that ellipse does change in its dimension over a very long cycle. It takes 100,000 years to complete that cycle. That's illustrated there at your top right. It's going to impact the distance between the sun and the Earth, so it does have direct impact on the amount of sunlight and therefore the temperature that we experience. But that cycle, because it takes so long to complete, again, is not going to help us understand temperature. That's how it's changed within recent decades. The axial cycle Earth's tilt is not perfectly vertical. It's tilted currently at about 23.5 degrees, fluctuates by a couple degrees over a cycle of 41,000 years. This is our best explanation for why we have seen periods of glacial advance and glacial retreat reoccurring on roughly that same time scale. There is a lag between when the axial tilt, how it changes, and how that relates to temperature on Earth's surface, but this has been well documented time and time again. And actually the trend of this cycle currently suggests that we should be trending toward cooler temperatures, and that has not really resulted yet. We also have internal variability within Earth's climate system, both atmospheric, oceanic. Usually these are very closely connected. The one cycle that you are most familiar with, at least by name, is El Nino and La Nina. This takes place in the low latitudes of the Pacific Ocean, and it really has to do with where the warmest temperatures in the Pacific are located. And that does change on the order of every few years, and it has direct impacts on the overall atmospheric circulation and does have impacts for us here in North America. Here in the upper Midwest, we usually feel it midwinter. During an El Nino or warm year, it usually means a warmer than normal winter for us. And during a La Nina, which we actually are now just entering, usually means a cooler than normal winter for us. So that is my seasonal forecast for you. Expect probably a cooler than normal winter if this La Nina persists. So those first four make up what you might refer to as the natural cycles. These have dominated climate change throughout most of Earth's history. We now add human activity to the list. Our population has grown over the last 10,000 years in particular, and our industrial revolution over the last, say, 250 years, that's where we start to play a larger role. So folks often ask me as a climate scientist, how can we determine if the climate change that we're experiencing today, how do we determine if it's tied to human activity or if it's still just the result of something natural? This is where climate models can become useful for us. I want you to focus on the top part of this figure first. The gray line is showing us surface temperature observations dating back to 1900, taking us through the present. You should see a similar trend what we saw there before. Warming the early part of the 20th century, stagnant temperatures from, say, 1940, the mid-70s, and then increasing temperatures since the 1970s. So that's just regular observation of temperature. Climate models are based on calculations. You have to be a computer programmer. Historically, it was in Fortran code. It's essentially based on the physics of the atmosphere, things like conservation of energy, conservation of mass, changes in water's composition, which phase, is it solid, liquid, or gas? And it's also based on the chemistry of the atmosphere and Earth's surface. And we plug in all these calculations, we give it some initial conditions, so we have to be able to provide it some initial observations, and then we allow that model to run either forward or backwards in time. Ultimately, we want to be able to use the models in a predictive sense, but before we can do that, it makes sense to run the models against one or more historic records so we can compare it to what has actually happened, so we can see how well the model performs. And ideally, you want to do this with multiple models and multiple time periods. So, the more confirmations you get, the more confidence you can have in the models. In this particular experiment, what they've done is they've taken a series of climate models and they've only input the information that we understand about natural forcing. So that's the first four bullets that we listed here. Things related to geology, solar cycles, orbital and axial cycles and things like El Nino, La Nina, and other atmospheric and oceanic cycles that we monitor. If we input only that information into the calculations and allow the model to run over this time period, the temperature that results is what you see as the black solid line. It performs okay in the early half of the 20th century, but then you can see that there's a clear divergence between the model and the observations after 1960 or so. You can see, if anything, the model suggests to us that temperatures based on natural forcing alone should be declining. If we take the same models and then add in everything we understand about human activity and how we're contributing to greenhouse gas emissions, and also how we contribute to land use change, things like deforestation and land cover change, things like changing forest to agriculture or grassland to agriculture, or forest or grassland to urban area. These things impact the way that Earth's surface absorbs and reflects energy. If we take all that information, add that into the model, that's what you see in part B, in the bottom portion. And you can see that it's a much closer fit now between the observations and the model performance. This tells us that now that we have all of the information, that the models can closely recreate reality. It confirms to us that human activity is the driving force of climate change, at least since around 1970 to the present. This exercise also tells us that now, if we add in human activity to our models, that the models perform quite well and give us a pretty good depiction of temperature. As you can see, it's not perfect, but it's a close estimate. And so if we were to take these models and run them for other time periods, either in the past or in the future, we can have a pretty strong confidence that the models are performing pretty close to reality. There's one more thing that we have to understand in regards to climate change. These are the forcings. Sometimes the forcing contributes a very small initial change in temperature. Contained within Earth's climate system are what we also refer to as feedbacks. Very simplistic feedback that you're all familiar with is the idea of the domino effect. You knock over one domino, and if they're all lined up appropriately, you should be able to knock over all of the dominoes without having to touch anything else. That first one takes care of the rest of the work. And there's some examples, not quite that simple, but there's some examples of feedbacks in Earth's climate system. There are actually probably dozens of these. Some of these we understand better than others. And this is one example. This is referred to as the ice albedo feedback. And the term albedo here has to do with the reflectivity of Earth's surface. And so we initiate a small amount of warming, let's say in Earth's Arctic area. We warm it by a small amount. That warming is going to result in some ice melt. So that's going to be changing the land cover type in that area. And generally, as we lose ice, we're going to be uncovering a darker land surface or water body. Ice and snow are lighter in color, so they reflect a lot, they absorb very little. But as we lose that ice, the reflectivity will decrease, here expressed as albedo. Reflectivity or albedo decreases, which means absorption is going to go up. So that's what's reflected in the bottom right box. And if absorption goes up, that means more warming. And if warming goes up, that means more ice melt. And you can see that this becomes a closed loop, which feedbacks on itself. All started by one small amount of warming. It then initiates further warming, creating further melt over the long term. There are multiple examples of these, some related to greenhouse gases, some related to clouds, But this is one of the more common examples, and this is the leading idea of why we see the most warming occurring in the Arctic compared to other areas on the planet. It has to do with this feedback in particular. Okay, so that's the science. We're going to talk about the solutions here. I'm going to pause and take a quick drink of water. If you have any questions, please let me know, or we'll also ask for questions at the end. Okay, let's move along then. So this is looking at environmental impact. And in this case, the impact that we're looking at specifically is carbon dioxide concentration in the atmosphere. And we can relate that to 4 variables. We have population with the crosses. And this is relative to its value in 1970. We can see that global population has increased steadily. Depending on the literature that you read, there's often a large focus on global population. All the way back to the 1960s, Paul Ehrlich had the famous book on the population bomb. And we can see that that population has been increasing steadily. The result of this, there's a couple of takeaways from population growth that we see here. Part of this is reflected by the fact that life expectancy has gone up. We are remaining on the planet for a longer period of time than we were prior to 1970 in the years before this figure. On a global scale, the number of children that women are having has decreased both in developed and developing countries. So although we see population increasing, fertility rates are on the decline really worldwide. Just in some areas, it's happening more quickly than others. In fact, some areas are seeing population decline. Places like Russia and Europe and Japan have seen population declines over time. If we look at income per person, that's gross domestic product or GDP, that's the solid black line. You see it's very closely following population. Generally, we would see that as a good thing. We want income to remain steady, if not go up per person. If we're trying to diminish global poverty, we need to see that closely related to population. There's very little that we can do to impact those 2 variables. And you can see they're increasing and they're impacting carbon dioxide emissions, because the more of us there are and the more that we're spending, that's going to mean more greenhouse gas emission. Where we have seen improvement is in the other 2 variables. And these are both in regards to our consumption and our technology uses and how technology evolves with time. The dotted line is referred to as the carbon intensity, that its units are carbon dioxide divided by energy. So it's a question of, for every drop of energy that we're consuming, how much carbon dioxide is emitted. It has to do with the efficiency of those energy sources. As those sources become more efficient, we emit less carbon dioxide. The dotted and dashed line, that's looking at energy intensity. That is the amount of energy we get out of every dollar we spend. And so again, that's kind of an efficiency variable. We've made some headway in both of these as we increase the efficiency of current technology, and as we move toward more efficient modes of technology, toward renewable sources of energy, we will see those 2 variables decline even more. These are really where we need to focus, I think, not just on a personal scale, but also on a national and international scales, focusing on these variables, because that's where the success has been and that's where it's likely to remain. Okay, so now, again, turning to global climate models, if we're going to now use these to give us projections out into the future, the trick about this is that we don't yet know what the future holds. We don't yet know for sure what the global population will be. We don't yet know what the sources of energy will be. We can make some guesses. Climate scientists refer to these as scenarios. We create climate scenarios, we provide that information into the model, and we run over a variety of scenarios so we can see the potential range of results. The RCP stands for Representative Concentration Pathway, and the number is the radiative flux added during each one of these scenarios during the Industrial Revolution. We're just showing you the values since the year 2000. This is showing carbon dioxide emissions in gigatons over these 4 scenarios. So the one that's closest to what we might refer to as business as usual, if we didn't change anything in our behavior, it would be the solid black line. Transitions toward renewable energy and transitions toward lowering global populations are going to give us the other 3 lines that you see here. So the most restrictive is RCP 2.6, giving you the light gray dash line there. So this is total emissions. If after our discussion today, you now know that the oceans and the plants absorb some of that, so the actual values and how this translates to the atmosphere is going to look different. So this is the actual concentration. Business as usual, by the year 2200, would take us beyond 1800 parts per million. Again, today we're around 400 or so. And then you can see the other values and how they reach kind of an equilibrium point at various points into the future. How this translates to temperature brings us to this figure. Again, the range of 4 different scenarios. Our literature often shows us falling somewhere by the end of this century within the range between 1 and 4 degrees Celsius. And here you can see that represented by the model projections. Following business as usual, we could expect this to be somewhere around 4 degrees Celsius. This is a global average, so some areas would warm more, and we'll show you that here in a second. With some transitions toward renewable energy, we might find ourselves somewhere in the range of the RCP 4.5 or 6, taking us somewhere close to 2 degrees Celsius. And that's a common benchmark that's referred to in the scientific literature today. Spatially, the temperatures will be felt differently. It's going to be most largely felt at the high latitudes in the northern hemisphere. Here you have the different scenarios, 2.6, 4.5, 6.0, and 8.5, and then over 3 different time periods, middle part of the century, the end of the century, and the end of the next century. Precipitation's a little less clear. This is looking at a projection at the end of the current century, increases in precipitation expressed in percent. If it's in blue and green, that means those areas will increase. We expect to see an increase here in the Great Lakes. Yellows and oranges, we expect decreases in those areas. The general takeaway is that the areas that are already wet, who already get a lot of precipitation, so that's going to be near the equator and in the mid to high latitudes, those areas should experience even more precipitation. And the areas in subtropical areas around 30 degrees north and south latitude, areas that are already desert and subtropical in climate, they're expected to get drier. And so like in North America, that would be impacts for the southwestern United States. And with the fires that we're already seeing in the western states, we anticipate that that issue is only going to get worse. So some common objections that I encounter as I'm out giving lectures or in conversation or in letters to the editor or in classrooms, they usually come in 1 of 3 forms, usually, or even more often, a combination of these. Those who are climate change skeptics might approach it from a science approach by trying to describe climate change as purely natural. I hope after our discussion today that you can see that although the natural cycles are incredibly important and have contributed to most of Earth's climate change over time, they do not explain the climate change that has occurred specifically since the 1970s through the present. It is almost complete 100% consensus from climate scientists that that's the case, that we can agree that human activity has contributed most greatly to warming temperatures since the 1970s to the present. There is less agreement about what has happened prior to that, but that one figure I showed you that gave us the difference between climate models running on natural forcings alone versus that had natural and human forcings, that kind of helped shut the door on that argument that used to exist in the literature. Arguments can also come from a religious side, the idea that a religious entity like God is in control, so there's really no impact from what we choose to do. My rebuttal to that is it's perfectly fine if you want to take a religious approach to this. But Christian literature still suggests that God has provided us free will, and there are going to be consequences from the choices that we make with that free will. So I think even if God is in control or some other religious entity is in control, there are still consequences from our daily decisions. Arguments can also be from an economic side, and the idea that renewable energy is often described as costing a lot. Really, all energy sources cost a lot, and really the expense is going to be determined by how we decide to subsidize those energy sources with tax dollars. Currently, we still choose to heavily subsidize the conventional sources of energy like coal production, natural gas production, nuclear energy. There are far fewer subsidies available for renewable sources of energy. If we could start to shift those tax dollars, that will decrease the expense on renewable energy up front. It's important to be careful about the information that's provided to you, and sometimes even more important, the information that's not shared. I want to use the example of this figure. If you look at the thin solid line first, it takes us from 1970 close to the present. A supporter of climate change science and the idea of global warming might provide you that data set to show that it's a clear increasing trend in temperature. I showed you a more complete record that took us back to 1880 toward the start of our weather network, because I wanted to show you the full picture. It's very common that folks will focus on just those warm years toward the last few decades. And you can see that the story with that information would be clearly warming, and you're making a clear message with that. The climate change skeptic can take that exact same data set and divide it, slice it into smaller pieces. You can see 7 different time periods were intentionally selected here to find cooling trends embedded within that overall trend. This is something that we've seen time and time again, where folks intentionally cherry pick the data to find the result that they want to be true. And you can say, okay, from this year to this year, temperature's going down, so the climate scientists don't know what they're talking about. And we've seen that even in recent years. This plateau of warm temperatures has a name. It's called the climate change hiatus, or global warming hiatus, because the argument is that the trend is no longer going up. That's not necessarily true. We're clearly at a plateau of warm temperatures. Many temperature records have been broken in the last few decades. This is not the complete picture either, because it's going to be biased on surface temperatures over land, because that's where most of the thermometers are. During that period over the last couple decades, much of the increasing temperatures has occurred within the oceans rather than over land. You go back to the figure earlier when I showed you ocean temperature, and you can revisit that. So going forward, really what we can do is, I think, 3 important pieces. We can continue to learn about these topics and climate change, and certainly I think I'm probably speaking to the choir, and that's why most of you are here today. We can talk about it. I do this every day when I'm in class with my students. We can make lifestyle changes on a personal level, and I think those are valuable and important, but there is growing information out there that suggests that most of the emissions come from a small percentage of the population. There's, I may have the quote not exactly right, but it's something along the lines of like the top 100 corporations are responsible for about 70% of greenhouse gas emissions, which tells me that for us to have a big enough impact on climate change and greenhouse gas emissions, it's going to have to be from the top down, from an international scale or on national scales from the federal level down through legislation. And from our end, really the only way we can contribute to that is by participation in voting at every election, not just the presidential elections, but also the midterm elections, also at your state and local elections. All of these have an impact. All right, so I want to conclude with you that I think they are recording today's lecture. I have recorded this earlier this summer. It's a slightly different version from what you witnessed today, but on YouTube I do have this lecture divided into 3 parts on the symptoms, science, and solutions. So if it's something that you ever want to take a look at again, those are the links on where you can do that. You also have my email there if you have any questions, if you have any interest in our geography program at Michigan State. I'm happy to help answer any questions in regards to their program. But before we conclude today, I want to open up the floor to any other questions that the audience has over our topics from today.
Nick asks if using solar energy can help decrease this problem.
Absolutely. Solar energy is most frequently used. Most of us think about it as a source for electricity. You install the photovoltaic panels, and that converts sunlight into electricity. You can purchase these panels to install on your own property or your business. There is growing popularity in leasing programs. I'm actually a participant in one here in East Lansing. They converted what used to be a former landfill into a park, and then they converted that park into a solar field. They installed, I think it's several hundred photovoltaic panels, and then the folks in the neighborhood were able to apply for a lease. It's like a 25-year lease, and it's per panel. So I think it was $300, somewhere in that range, and you could pay it over the 25 years, or you could pay it up front. And then whatever electricity that panel generates over the month, that gets discounted from your utility bill. In my case, it's from Lansing Board of Water and Light. We only have one panel, so it only gives us a couple dollars a month, but over the course of that 25 years, it will actually be a financial profit for us. Solar energy can be used also for water heating. Most people are less familiar with that. It's a system that you could install usually on the roof of your home or your business. It's usually black, so that maximizes absorption. You usually still have a regular water heater, but it's kind of in supplement of that. I had my PhD advisor when I was in Michigan State. He had one of these systems installed on his home, and in mid-Michigan, he said for his family of 4, they really didn't have to use their water heater at all. From about mid-April through mid-October, their water was pretty much exclusively heated by sunlight, and then they used their water heater during the winter months.
All right, well, I guess that's about it for us. Thank you so much. That's actually super, super interesting that you talked about that leasing of those plots. That's genius. That just sounds amazing.
I hope more communities can get on board with that.
Yeah, absolutely. Well, we want to thank you so much for hosting this for us today, and I hope everybody was able to learn something and can take something, pass it on. Again, make sure to check out his YouTube series if you want to see this again, and there's his email address is there if you have any more questions that you think of after today. So thank you so much, Ryan. And have a great day, everybody.
Yep, very welcome. Thank you, everyone.